Okay, so picking up right where we left off, we just did this example. Hey, it actually all fits on the screen just about. Um, we answered this way and we used those absolute values, and then we worked with that. We were able to work with some algebra, factoring, dividing to get that value of x. Okay, we just saw that example. Here's where we want to go with this next. We're going to generalize that process that we just saw. Let me move it all the way up. We were using 0.1 away from 7, and we realized that we needed to be 0.025 away from 2, that x had to be 0.025 from 2. Before we get to the precise definition itself, we need to, I think generalize is a good word. So instead of using specific values like 0.1 and 0.025, we're going to use variables. Okay, so we're going to generalize for any small distance, and there's this, Greek symbol, Greek letter epsilon. It's their letter E. I don't know, you may or may not have seen that Greek letter before. That's a lowercase epsilon, by the way. Any small distance epsilon from 7 and delta from 2. Okay, so the delta, it's kind of like a script D, kind of starts here and curves around like that. So the fact that the concepts in this section use these funky Greek letters certainly does not help the conceptual side. You know something's difficult when it uses funky foreign letters that you haven't used really. All right, any small distance epsilon away from 7, the function will be epsilon away from 7, and x will be delta away from 2. So what would this look like if we wrote it out? Again, we're sticking to that same example, still using 4x minus 1, that same limit equaling 7, right, as x approaches 2. So here's what it would look like for any small distance epsilon. So before we were using 0.1 away from 7. And we had a 0.1 here. But now we're using this variable epsilon that represents any small number that we like. Okay, so we've got the absolute value, 4x minus 1 minus 7, less than epsilon. So the difference between our function and 7 is within epsilon. Okay. Now we're going to walk through the same algebra steps that we just did. We're going to simplify this left side. Okay. Simplifies the same way, right? 4x minus 8. We're going to factor out that 4. That all looks the same. Finally, we're going to divide by that 4. And I need another piece of paper for that. Maybe I'll try and keep all this on the screen. Okay. So we can see the flow. All right, we're going to divide by that 4. Okay, so we've got epsilon divided by 4. So at this point, when we're using 0.1, right, we just did the division and we had the answer. But now, right, obviously with epsilon, we're just going to say epsilon over 4. But that is how close we need to get to 2. Okay, if you want to be within epsilon, your function within epsilon of 7, then x needs to be within epsilon over 4 of 2. Let me say that again. I'm going to scroll this down. Let me write it off to the side here. X needs to be within epsilon over 4 of 2. And you can see there that that's what delta equals, because delta describes how close we need to get to 2, how close x needs to be to 2, delta will equal epsilon over 4. Now this is a big step forward. We're almost ready for the precise definition. What are we saying here? I'm saying no matter what value you pick for epsilon, if you just divide that by 4, whatever value you pick, divide it by 4, that's how close you need to be to 2. If you want your function to be within 0.1 of 7, then just divide that 0.1 by 4. That's how close you need x to be to 2. Hey, maybe you want epsilon to equal not 0.1, but 0.01. All right, if you want your function to be within 0.01 of 7, divide it by 4. And that will be how close x need to be to 2. What is 0.01 divided by 4? Just 0.0025. And you could pick epsilon to be as tiny as you need it to be, or as you want it to be, and we can very quickly, with that relationship, find out how close x needs to be to 2. Okay, so what we really are after is that relationship between epsilon and delta. That is critical for the precise definition of a limit. Okay, whatever you pick for epsilon, in this case, divide it by 4. Hey, just curious, here we're dividing by 4. I'm actually going to go back, go all the way back here. This is where we began. That's the function, right? And what's special about the 4? I mean, we see the 4 right there. I mean, what is that? I mean, the function is f of x equals 4x minus 1. What does that 4 represent? You might say, oh, this is a line. That's the slope. The slope of that line is 4. Yeah, so if it's, if the slope is 4, then that ends up causing that relationship between epsilon and delta. Okay, anyway, in case you didn't notice that, it's good to point out. Okay, so here, this is where we were. We know the relationship between epsilon and delta. Okay, why is that such a critical breakthrough? Okay, this is going to lead us, this is the heavy concept that's going to lead us to the precise definition. However close we require 4x minus 1 to be to 7, there is a value of x close to 2 that will make this happen. And then we can say that the limit of 4x minus 1 as x approaches 2 most certainly equals 7, and nobody can argue that. And it's incredibly precise. It does away with this idea of approaching, which is ambiguous and debatable, and it lands us in something that nobody can argue. Why is that? So imagine, right, imagine your function and somebody's saying, hey, I know that when I plug 2 in, I get 7, but with limits, it doesn't matter what actually happens at the x value. All that matters is what's happening as you get closer, or what happens as you approach. So how do I know that the closer I get to 2, this really will get closer and closer to 7? Because, I can look at a graph or something, I can plug numbers in, make a table, but how do I can't trust my eyes. I can't trust plugging numbers in that are close to 2. Because still infinitely many things could happen in there, and visual inspections are my eyes could be deceived. And somebody could say, okay, well, we know this relationship. We've shown this relationship holds. Nobody can argue that relationship. So however close you need this function to be to 7, just tell me how close you need it to be. I'll divide that by 4. That's how close you need to get to 2. And that works for any number, however close you want to get. And if it works for every number, then there's no limit to how close you can get to 7. If you get closer to 7, then x just needs to get closer to 2. If you need to get even closer to 7, then that means x just needs to get even closer to 2. So as x approaches 2, I know for sure this function is getting closer to 7. There's no doubt about it. And I can tell you how close you need to be at any given moment. And if I can do it at every moment, then it must be. Okay, I'm going to stop there. Hopefully that makes sense. I'm going to show you this idea graphically. Okay. And it might make total sense to you, but maybe this graph would help anyway. Or if it doesn't make sense yet, maybe the graph will kind of give you a new light on it. Okay, so here we have graphed f of x equals 4x minus 1. And I've gone ahead and plotted 2 and 7. Okay. So here's what's going on. Let me sharpen my pencil. I've created this little boundary around 7. So I could get a little bit bigger than 7 or a little bit less than 7. Okay. I'm going to say this is 7 plus epsilon. That little distance is epsilon, which would make this 7 minus epsilon. I could move epsilon in either direction. Okay. So what I found algebraically a moment ago was if I draw this line out to the function and then I drop it straight down, it's going to be a little bit less than 2. Right? And if I draw this line straight out and then straight down to the axis, it's going to be a little bit more than 2, and it should be perfectly symmetrical. My drawing's a little bit funky, I guess. So what's cool is this creates like a little zone around 2. Okay. So if I want to fall within this interval, well, then I just need to make sure I fall within this interval of 2. And now I can shrink that down as small as I want it to be. That's just going to mean this interval needs to shrink down. But there is a ratio between them. However big this is always exactly 1/4 the size. So if this is 0.1, then this is 0.025. One width of it would be half of it. But if I make this epsilon little window smaller, tighter, then that just means I close in on 2. There's no doubt about it. As x gets closer to 2, that function gets closer to 7, just the way that these squeeze together. This right here would be 2 plus delta and 2 minus delta, and we found that delta equals epsilon over 4. Okay, let's conclude this video with me sharing what the precise definition of a limit is. We'll get to more examples in the next videos. Here it is. Don't be overwhelmed. We're going to say the limit as x approaches a for the function f of x equals L if the absolute value of f of x minus L is less than epsilon for every epsilon greater than 0. Okay, let me read that part again. If this is true for every epsilon greater than 0. Why do we say greater than 0? Well, epsilon is always positive. It's a distance, and it will never equal 0. So if the distance between these is less than epsilon for every single epsilon greater than 0, there exists delta greater than 0, also positive, such that the distance between x and a is less than delta. So as you approach a, you come within delta, then we know this is going to be within epsilon. There's your precise definition. And it takes the same form. Okay, we're going to see an example in the next video using the precise definition. It's actually going to look very similar to things we've already done, but now we've kind of come full circle. Okay, I will see you there.